Hi everyone. So we're going to do a bit of talk about Ceph with CloudStack. My name is Andrija or Panic if you would like to read it, but I have a trademark there, so keep that in mind. Before I continue, I would just like to ask everybody that it would be actually really nice if you could join us for the hackathon tomorrow in the same rooms. So it's very relaxed and kind of atmosphere, just sitting down and discussing different things, simply seeing what are the problems, how to move forward, and so on. And I would also like to ask whoever is actually allowed to or capable to actually participate in a very 5 to 10 minute short interviews, because we are doing CloudStack marketing video to try to move things even more forward than they are actually right now. So that's also going to be during the hackathon, probably around lunchtime or something like that. So it's very short, so whoever is CloudStack user, like the guys from the Leeds web or whoever is willing, it will be very nice. Good. So yeah, my name is Andrija Panic. I'm working for Sheblu, started recently, and I'm located in Serbia. At the moment, committer and recently appointed to be a PMC member. But I've been involved or actually worked with CloudStack since the 4.0 incubating version, the first, let's say, kind of official version from Apache Foundation. And in very short, that's about me. I'm going to give a very quick Ceph intro about architecture and stuff, but kind of very quick. Now, I do need to kind of mention that this will be more, let's say, Ceph-oriented. There will be more Ceph-oriented content, but in relation to CloudStack and some general considerations. But we're also going to cover, obviously, adding it to CloudStack and touch a couple of things there. Good. So a bit of fun facts, if you like, from Wikipedia, and the reason why actually Ceph was named like that. Sage and the guys thought it has to do something with a multi-tentacle distributed physiology of the cephalopods as the kind of vertebrates. So that's a bit of on the living world. Moving to a more IT world, if you like. You already all know it's effectively open source distributed software-defined solid solution. Initially, the whole idea behind Ceph is that it's meant to be scalable up to many tens of thousands of nodes without any kind of single point of failure, and to be self-healing, if you like, or self-managed whenever possible. Which means when you have dead data disk, object replicas will be automatically recreated on another OSDs or actually drives, if you like, of whatever kind you're running. The whole thing is built around the crash algorithm, which effectively stands for controlled replication under something. The thing is that you do not have any kind of lookup table for metadata and stuff like that. The whole thing is that actually, in order to read data from that you like, all the client and the, let's say, server side, meaning the Ceph cluster, and the clients being Ceph clients like librd that's being used by libvirt and Camu, they all know by the hashing algorithm, specific hashing algorithm, by the crash algorithm, where the data is already located, so they can speak to a specific OSD node, which I will explain briefly, and fetch data. Or when it needs to write data, it actually knows where to write the initial copy of the data. So there is no lookup table or file system table like with all normal, let's say, file systems. So that's what makes it pretty powerful. It does provide a couple of access methods. So we have a file and directory, let's say, based, which is Ceph file system. We have, and what we are actually consuming through CloudStack is the block level or the RBD or the Rados block device image, which is effectively a virtual volume, which can be accessed also not only via native Ceph client, RBD client in some way, but it can also be exposed via iSCSI gateways. Or there is also a third-party NFS Ganesha, if I pronounce it correctly, software, which is effectively kind of an NFS gateway. So you can export Ceph file system via NFS gateway and connect your VMware, for example, because VMware obviously and Microsoft solutions and stuff like that, they don't have native client for Ceph. Native Ceph client. Yeah, that's kind of it. And obviously it does provide object storage, so S3 and Swift and Swift being a supported protocols. So how it looks like on architecture side. The foundation of the class of the, let's say, the whole Ceph thing is the Rados cluster, which stands for what you can actually read, something object store. So reliable, autonomous, distributed object store. The whole thing is that it's an object store. It does have a librados, which is effectively an API level access. It's providing API level access to the cluster. And you can build it does provide obviously, bindings for C, C++, Java, Python, Ruby, PHP and stuff like that. So you can build your own applications, which is kind of a first square over here that will talk to the librados. Example of that is, for example, Rados Java library, which was written by Guido to handle some snapshot stuff because libvirt via librbd, which I'm going to explain later, doesn't yet support managing Ceph snapshots. So we had another external utility which is talking directly to the Ceph cluster via librados. Obviously we have Rados gateway, which is effectively translates S3 and Swift calls, if you like, API calls to a librados calls, and effectively storing objects on the object store or the Ceph cluster. For example of those are obviously S3 clients of any kind, or some specific Swift clients and stuff like that. We have RBD, which is a Rados block device. Effectively, it provides virtual volume for a VM, which you can consume via KEMU, which uses librbd as the Ceph client library on your KVM host, or you can actually map the volume, this virtual volume, via either kernel image or RBD NBD utility via effectively NBD driver to your host, whether a VM or a physical server. So, there are a couple of ways to actually connect it like a raw block device to Linux specifically. And finally, we have a Ceph file system, which is kind of in the development for a long time and became officially stable maybe 2-3 years ago. Don't quote me, but something like that. And it can be exposed either via native clients or kernel clients and Fuse, let's say client, or it has support for being mounted via Fuse. Or you can actually export it via Ganesha NFS, as I already mentioned. So for compatibility reasons to VMware, to Windows, to, Zen, or actually whatever you like to use. Not the best performance when you're using NFS gateway, so it's not like your enterprise NetApp stuff. Keep that in mind, but it is there, and yeah, it's interesting in order to be able to access the stuff via NFS. Very briefly, Ceph storage cluster, which is also called Rados cluster, is effectively based upon Rados, which is something object store. Makes sense. It does consist of two types of mandatory daemons, which are Ceph object storage. I'm going to explain this briefly, and Ceph monitors. Optionally, if you're using Ceph, or if you want to have Ceph file system, then you also need to install the Ceph metadata servers, which are, as you can suggest, tracking and keeping metadata of the actual data that you put on the files, directories that you put on your Ceph file system. Minimal possible installation, obviously, will have at least two OSD daemons, which means kind of two OSD, two storage drives of whatever kind, because of the minimal replica being two, which means one original, one replica, total of two replicas. And also it will have, it needs one monitor to keep all the tracks of everything, which I'm going to briefly mention. In production, I was, for example, a couple of years ago managing in production a Ceph cluster of 6 nodes, and not the best setup, especially if you go with hard drives, with a mixture of hard drives and SSDs for journals. Not the best performance, but we are going to touch that later. A lot of our actual community users would suggest 10 storage nodes at minimum, and which means kind of 80 plus OSDs, which translates to a single SSD, single NVMe device, single hard drive, kind of 8 or to 10 to 12 per node. OSD nodes are effectively just a physical node which you put where you have actually many OSDs. That's kind of a terminology. And OSD, as already expanded, stands for Object Storage Daemon, which is effectively managing a single storage device, being a hard drive, SSD, and stuff like that. For OSDs, you can have like up to 10,000 or not up to, actually tens of thousands of them in the cluster. It is managing a single hard drive, SSD, and NVMe and stuff like that. They are the ones who actually serve the objects from the Rados cluster, so something object store. They're the ones who actually serve the data effectively to the clients, while monitors actually provide just the cluster. I mean, it's very kind of intelligent and complex work. They contain all the cluster maps, which are kind of 5 different maps, which are sent initially to the clients. Ceph clients do connect to monitors to obtain the cluster map, who is alive, where the data is, what PGs are there, which we're going to briefly mention later. So simply to learn the topology of the cluster, and once the client has learned this or got that data from the monitors, they will actually then by simply being a crush algorithm enabled clients, they will know to which OSD to connect to read existing data or to write new data to. The small image we effectively represents many different servers. For OSDs, you will have many OSDs per single server, physical server usually. But for monitors and metadata servers, you can have only one of those daemons per physical host or virtual host. And for that matter, you actually can use and probably you would use VMs, not wasting like extremely powerful server, but they do need to be of a decent performance, especially in larger clusters. In this example, you have like 3 monitors, which is kind of a minimum. For redundancy, it's a minimum recommended. It has to be odd numbers, so 3, 5, 7. Most of the users on huge clusters will not use more than 7, because that's already 7 times redundancy in sense of having 7 different monitors. Because the more you get, the more communication there is exponentially, and there is a lot of noise in that sense. So you don't want to go like more than 7 usually. Good. So extremely quicker than so far is the Ceph installation process. We're going to just mention briefly a preparation, installation process, and then more interesting, possibly in sense of being of CloudStack. Let's say to create a pool and add it to CloudStack. So let's jump forward. The preparation is obviously a couple of things that you need to do. Ceph is extremely sensible to time difference between servers, so make sure to have this really tightly synced. And later I'm going to do a very short demo, and I'm probably going to have my servers not synchronized, just to show you how it works. Obviously, fully qualified domain names, which is a kind of a full host name, needs to be resolved between all the cluster nodes. And usually when you're building a Ceph cluster, you will have one dedicated small VM which we call the admin node, where from which we actually deploy whatever tool you are using. Here I'm going to just show you the very, let's say, old and perfect for a demo and POCs installation Ceph deploy tool. But in production, you would probably use Ceph Ansible or Rook, whatever it's actually pronounced, and stuff like that, to be able to actually do a much better job of automation. So make sure that the name is resolvable, make sure that the SSH key-based authentication is working from the admin node to all the cluster nodes. No need between cluster nodes to have that, it's not consumed. And also add the proper Ceph repository for Ubuntu, for CentOS, whatever you're using, on your admin node, and finally install. Once you have the repository, simply do yum install or apt-get install Ceph deploy tool. That's on your admin node. Now, the actual installation is obviously on the admin node. You would like to create a folder where you install your cluster definition files and where you will keep your Ceph configuration files, from which you actually distribute over to the Ceph cluster nodes. Make folder, go to that folder, use the Ceph deploy new command, defining initial nodes. No configuration or installation is done so far. It will just make the cluster definition locally on the admin node, but it will connect via SSH just to verify access and gather some other information, but no changes so far. Ceph deploy install command will actually go install binaries on the hosts which you actually provide on that command line. Now, for this latest, this whole, let's say, POC or setup I was doing with the newest Nautilus release, 14.2, Ceph deploy for now, at least in that moment, wasn't actually, let's say, updated to by default use the Nautilus, which is actually what it should do. When you do not specify the release, it installs the most recent stable release. So I was here just explicitly mentioning release Nautilus. And finally, once the binaries, but only the binaries are there, nothing started, no daemons running, nothing, just yum install was effectively done. You would do the Ceph deploy mon create initial, which effectively takes all the nodes from the cluster definition file, which was created in the first step, and create monitors and effectively forms your cluster. Now you do have a cluster already, but there is no SD daemon, so kind of not yet useful cluster. And finally, what you would do, you would actually, or not finally, actually, there are two more steps. You would deploy the needed keyrings and the Ceph configuration file, which was created during the first command, to all your cluster nodes. And finally, on each of the cluster nodes, you would effectively, assuming that the dev SDB is your data disk, in my POC, it's only one drive, one OSD per node, which is definitely not something you will do. But for the POC, you will simply say Ceph deploy, OSD create, and then path to the actual device. And this time, effectively, you do have your cluster running. Obviously, this is just a POC, but there is a lot of more you would like to, with additional tunings and stuff, you would actually do in production. That being said, in previous release Mimic and now new in Nautilus is the dashboard, which now comes as in Nautilus as a separate packages, which are not still handled by the Ceph deploy. So you do need to locally log into the cluster nodes and do the yum install, and then only one from any of the cluster nodes you will say for the POC again, not something you will do in production. You will disable SSL. Enable the actual dashboard module, and finally create your admin/password as the administrator role access, and have your dashboard running. The reason I'm recommending your dashboard, because in Nautilus, in previous releases before Nautilus, it was mostly read-only, but now it actually became extremely powerful, and you can do many different modifications. I will briefly walk you through this in some of the next slides. So it's a very useful stuff now. Finally, before we touch the dashboard, the required steps are obviously to create a pool for the CloudStack, set its replica size to, in production, always 3, not 2. New things in a couple of last releases, we need to initialize the CloudStack, and also a new thing in contrast to older releases is a little different syntax to create effectively a client keyring for that specific pool. We got one user on the mailing list who was actually using an older syntax on the newer cluster, and then some of the features were not working because simply he wasn't using really the latest documentation to create the or maybe he upgraded something like that. So there was a need to actually modify his keyrings to actually be able to utilize some of the newer features like exclusive locks and stuff like that. Example key of the last command will be given just on the standard output, so write it down obviously. And before we proceed, we do have a key which we can consume, but let's configure KVM caching, which is something you absolutely and definitely want to do on your KVM nodes. Usually we'll keep the identical Ceph.conf file across cluster nodes, hypervisor nodes, but this is for now technically needed only on the KVM nodes. Enable cache, very important for older Linux kernels and in general older Virtio drivers, is you want to say activate for write through cache until I receive the very first flash command, because in older Linux kernels like 2.6, CentOS 6, some versions of CentOS 6, the Virtio driver was not sending proper flashes, and then if you have a write back cache and no proper flashes, you lose for whatever reason, electricity or something like that, you end up with a corrupted image and you can throw that VM away. So only after we receive the first flash request from the Virtio driver, from the storage driver, after Ceph receives that, it will say, okay, this is a smart enough client, then I'm activating write back caching, but before that it's only write through, which effectively is not a cache in a sense. And we will, once we populate this data to the local Ceph.conf on the admin node, we just want to propagate again this Ceph configuration file to the KVM nodes. Obviously, make sure that the SSH is working, the names are resolvable, things like that, similar to the nodes. Cool. Moving to a very short dashboard demo. Give me just a second to move my window. Left or right? Probably right. Cool. New Ceph dashboard. Let me refresh that, but probably that's pretty much it. You will notice I'm not green anymore. I have a health warn, and if I click it will say clock skew detected on monitor KVM3. I'm using KVM nodes in my POC, but this is Ceph cluster node. Once you do a proper NTPI update, because I do have some issues in labs, in the lab in sense of time synchronization, so I need to keep it from time to time. Anyway, once you do that, it will be fine. Very useful thing is that be gone. You have a couple of sections in this. Obviously, in the first dashboard, you have a different cluster status for monitors, for OSDs, for the cluster itself, for different daemons, for object gateways and stuff like that. You also need your performance section. Obviously, my POC cluster is not very busy, but you can monitor client throughput and IOPS versus recovery throughput, which is very important thing to kind of throttle properly in production. I will touch on that later. Also, you can see any scrubs which are effectively file system checks like checks, but for the OSD daemons. So it's checking the data, which means scrub effectively is, let's say, file system check in a way, although there is no file system now with these newer Ceph releases, which I'm going to touch again. Capacity of different kinds, objects, PGs, status of PGs, which means effectively health, not really capacity, but it's there. So again, very, very useful thing. What you can do, you can observe your monitors, OSDs, you can scrub your PGs, do deep scrub, reweight your OSDs, so do many modifications of the OSDs. You can also set up a cluster-wide flags as needed. You can observe performance, read-write bytes and IOPS per OSD. You can observe overall performance, but notice that I didn't enable the Prometheus metrics exporting, if you like. So my dashboard cannot consume this because the sources are not there for the data. But once you do that, you will have very nice metrics available. You can also do a bit of cluster-wide configuration, which for some reason is taking time. Change a couple of things. You can manage pools, create pool, delete pool, edit pool, observe performance again on a per pool basis, and stuff like that. Very useful. You can manage your block devices, which are effectively RBD images that our CloudStack is using. Do different things, obviously, create, edit, and stuff like that. A bunch of now with Nautilus it became very, very powerful dashboard in the sense that you can actually change and manage things in contrast to previous, and also you can also manage NFS Ganesha once you do a couple of preparations on your Ceph cluster manually, object gateways and stuff like that. So again, very, very powerful dashboard in these new releases, so that's the reason I'm kind of mentioning it. But this is a bit more kind of complete list of the changes in the dashboard itself. So really awful a lot of interesting things, good stuff. New in Nautilus, not in dashboard, but in general, there is a lot of things which I won't be touching because I'm pretty sure I won't have time to cover everything. But at least in your production, you will need to open, possibly some additional firewall ports because there is version 2 protocol of the monitor communication, which finally has a properly assigned, official port instead of previously used one, which was not IANA, if I pronounce that correctly, approved or assigned. With encryption and things like that. So a lot of different things like smart prediction failure, optional automatic migration of your objects away if it predicts that the drive is failing. So really awful a lot of interesting things. And also they do a lot of work with Rook, which is effectively an operator in Kubernetes, to be able to extremely easy, like with 3 commands or so, to spin your demo cluster for testing purposes and stuff. They're still doing some work to make it kind of production suitable, but so far mainly people were using Ceph Ansible as the proper tool for managing production clusters. Good. Let me just check my slides. I believe I did skip something. Sorry, I did not skip anything good. Next thing, once we have a pool ready and so on, you will obviously add your Ceph cluster. Not needed to say you will create an offering and spin a VM. But in sense of adding, where did my mouse go? In sense of adding Ceph to the CloudStack as the primary storage, you need to choose RBD as the protocol, define monitor, which I'm going to touch just now, define your Rados pool, which we created by its name, user and authentication key, which was output to your standard output, optionally do RBD tagging, storage tagging and things like that. For the monitors, you will never ever obviously define, if you have like 3 or more monitors, you will never define a single monitor, because if that monitors go down, your KVM host cannot no more speak to the Ceph cluster, so it's kind of not really good setup. For demo cluster, this is what I did, but what you will do in production, will create a round robin DNS entries in your local DNS, hopefully local DNS. So it will resolve, randomly across 3 different IP addresses. If one of the monitors is dead, you will rush to your DNS, remove the entry, and you are kind of good to go. So that's how the things are used in production. Unfortunately, you cannot use, for example, whatever HP proxy or some other proxy to monitor the Ceph monitor traffic, because the messages are signed and you cannot actually interfere with the packet. So that's the reason why you cannot actually use local bouncers, which is the first thing in my head that I would use if it would work. So let's observe a couple of things. Once you spin your VM, how to locate your images on the disk, do some checks, or simply see how they are organized. When you create a new volume in an existing Ceph cluster, obviously in the database, in the volumes table, you will have a path field. This path field is for the new volumes, which are created from zero as opposite to migrated from somewhere else. The ID, the path will inherit the value of the ID, so it's very easy just to go to the GUI, check the ID, and then you will go to your Ceph cluster, either list the images and notice the same ID, this is actually UUID in the database. In the GUI it's mentioned as the ID, or you can simply set RBD info, and then you say pool/image, which is, our pool is named CloudStack/image, and you will get some info about that specific CloudStack image. Different things over here, but the one I would like to kind of, in the sense of this presentation, focus on is the parent image. As you can actually see, effectively there is a parent image which is actually a snapshot of some other image. So, what are we actually talking about here? Let's see. When you create a Ceph, brand new Ceph VM or a volume from a very first time from a template, the usual thing happens. So effectively, the image will be QCOW2 image. Will be converted by the QEMU image utility. The KVM hosts are the one doing the work. They will convert the QEMU image from the secondary storage, which is mounted obviously on the KVM host, and stream or write that as a new image on your RBD cluster, creating this template image OA7. If you go back, that's the one, OA7. So once it's done, it will create a snapshot, give it some hard-coded name, but the name is obviously not important. In sense, if you do it manually, it will protect it, and only then it will create actually the VM for your, this is FEB, if you see over here, that's our volume. Only then it will actually create the actual volume. The thing that it does protect the snapshot is that you cannot go and really delete it. So that's the nice thing. If you want to actually see all the volumes, not via database, but in reality, on your Ceph cluster, on your storage, actually, you can use the RBD children command and then define the pooled image and then add snapshot name, effectively asking what are the children images. What are the children images of my snapshot over here, which was created in the previous step, and you will see many of those, including the one that we were showing so far. Just for fun, how would you manually reproduce that behavior? Actually, you would either use the QEMU image to convert QCOW or RBD import to convert to QCOW and write it as the new image, or for the sake of simplicity, you would just create an empty image. Do the snap create command, which creates a snapshot, giving it name. So you have to give it some name, doesn't matter if it's really this one or the other. But then you will protect the snapshot, and finally you will do the RBD clone command, defining the source snapshot, and then the destination volume, obviously in a form pool/image. So that's what you can do just for exercise if you have nothing else to do in your life. And the cleanup would be completely the reverse. So effectively, in order to remove the original image, you cannot remove it as long as it has snapshots. Now you cannot remove the snapshot because you haven't yet unprotected the snapshot, and you cannot unprotect the snapshot if you still have child images. So the steps are really to remove all the volumes, all the child images, unprotect, remove the snapshot, and finally remove your template file that was created initially. Good. So a bit of hacking under quotes. If you would like to actually mount your RBD image on your Linux, doesn't matter obviously if it's a VM or a physical host, you can either use the kernel client with the RBD map command, defining pool/image. This short syntax does, like in other examples, for the other tools, it does imply that you have on your client, on this node where you're actually mounting this, that you do have your Ceph configuration file and the needed client keyring file, which is authentication file effectively, which contains the user and the secret, in the default /etc/ceph directory. You can see a different thing later, I will explain that. But the problem with the kernel client, for some reason which I really don't understand, is that it's always lagging severely with its capabilities behind the current version of the cluster. So, for example, I did install from LRepo kernel on the Linux version 5.0 of the kernel, and I still couldn't speak to my Mimic cluster, and leave alone the newer Nautilus cluster. So, the client image is kind of useless in most of the scenarios. Unfortunately, it would be nice if the guys would actually keep their pace with the actual cluster thing. What you can do, you can use the RBD NBD utility, which is part of the Ceph repository. So if you have installed Ceph, you already are able to actually install that utility, which actually uses the NBD driver, which for some reason is not part of the stock CentOS kernel. So you either need to compile the kernel and extract the image, or you can install LRepo kernel for a CentOS, which does contain the NBD driver, or you can use Ubuntu, which is not my personal favorite operating system, but it does have all of this stuff. Once you do that, you can simply map your image. This is using librd. Qemu is using librd. So librd is effectively a user space client for Ceph for speaking to RBD instance of RBD images, or rather block device images, or virtual volumes if you like. That's the thing. You need obviously to install the stuff and mod probe the NBD before that, and then do the RBD map command. If you have done loaded the needed module, you can also use Qemu NBD, which is installed by default usually when you install KVM, and simply connect your pool/image as NBD device, and effectively this becomes just your local raw block storage device, and you can do whatever you want with it. You can mount existing images like that, even if that image is already attached to a VM. So, if you need to do some low-level troubleshooting, and you can do that. Not really good for privacy, obviously, but yeah, that's what you can do if you don't have, in the existing VM images, if you don't have encryptions and stuff. With Qemu image, you can do Qemu image infor, Qemu image convert, which is effectively all the copy operations between the secondary storage and the Ceph cluster are done by Qemu image utility, which the KVM hosts are executing, usually one randomly. Actually, let me rewind that. It depends in different situations which KVM host is doing the work, but anyway, the KVM host is the one doing the work, not the secondary storage, for example, like in case of VMware. Again, short syntax implies you have your all your data in ceph.conf and authentication key, or you can use this, let's say, ugly command. You need to define your monitor host. You need to define that Ceph X is the authentication method. You need to define your ID, which is a user, and your key. This only requires that you have the librd as a Ceph client enabled on that particular host when you are running the Qemu image command. So you don't need to have keyring, you don't need to have your Ceph configuration file, and things like that. Some limitations around, I can say Ceph, or actually any, when you pass any kind of raw block storage to the Qemu VM, KVM VM, it is not possible to do VM snapshots. So VM snapshots are only in KVM world possible with QCOW2. So, if you're running NFS or local storage or some other kind of file system base where you can put your QCOW2, that's only the situation setup where you can actually create VM snapshots. But you can do volume snapshots as with any other, obviously, hypervisor in CloudStack. There is no there is some work being done there, or will be some work done then There is no support for the storage heartbeat file. You have this kvm heartbeat.sh or Zen server heartbeat.sh, which will reboot the kvm host, assuming that your storage is the one which is highly available if it cannot access the storage. So there will be some work done there. Also, it is currently not possible really to restore a volume from a snapshot. So prior to 4.11, for any kind of storage, the only way to restore volume snapshot was either to convert the snapshot to a template and spin a new VM, if it's a root disk snapshot, or convert snapshot to a data disk and attach it wherever you like. So effectively creating new resources, which is not really a way to restore quickly your data. But starting with 4.11, if you're using NFS, there is actually a very nice restore button and API, so you can actually revert to that snapshot. This does imply that you keep your snapshots on your primary storage and they are copied over as well to the secondary storage. Actually, this is implemented, I believe, also for Ceph, but it's being buggy for some reason. So some of the guys are actually taking care of this as we speak. Also, just to be aware that there are two external libraries when using Ceph with KVM. Let's say partially it's not related to CloudStack. So, with your QCOW2, you have your storage, you have your KVM stuff or QEMU stuff, libvirt, and you don't care. Here you also have librd, which is kind of a Ceph client, user space client that QEMU is using to actually talk to the Ceph cluster. And we have, as already mentioned, a specific Rados Java library, which is obviously a tool, a library written in Java to be able to manage some snapshots functionalities on Ceph as required by CloudStack. So not actually too many of the limitations, except, and that is actually for some users a big limitations, not being able to create VM snapshots. Learning curve can be pretty steep, depending on whether you want to do that yourself or not. What I would definitely kind of advise, if I'm kind of allowed to give advice, is make sure that you have proper know-how on the Ceph, either in-house or support with some of the guys. God forbid Red Hat, because it's very expensive, but you have some other companies which also do provide Ceph consultants and support, because sooner or later you might need it. And also make sure that you have really good troubleshooting skills, because everybody can spin a new cluster. It's very kind of a easy use, so a very really simple demo. But when it comes to troubleshooting, you really need to understand very low level things, in order to be able to save your clients from the downtime. In certain cases, I'm not implying that there is always like this. It's absolutely not, but there will be sooner or later some of the issue. Simply, it's a very complex and distributed storage, so you definitely want to be prepared, for that moment. Also, a very specific thing which I personally wasn't aware when I started my Ceph journey like 4 or 5 years ago. When your OSD goes down or you add new OSD or things like that, object replicas will be either regenerated as a copy of existing replicas or moved away, simply migrated away to other OSDs and stuff like that. There will be a lot of recovery, which is that's the name, which is used, recovery traffic, although maybe you just added new drives, but still, based on the crash algorithm, Ceph will say, okay, I have a new OSDs, now this setup, I don't like it, let's shuffle some objects around. And it will cause a lot of objects being, not a lot, but, some portion of the objects being moved around. And this is kind of named as the recovery traffic. So you want to make sure that this recovery traffic is of a very low priority in contrast to the client traffic, because if you have a lot of throughput which kills the client I/O, your client I/O will get very slow, and you will have a lot of complaints from customer, up to the point that if the I/O was not served for up to 30 seconds or something, that in extreme cases some file systems will remount as read-only. So just keep that in mind. Performance considerations. It is said that Ceph works on commodity hardware, and it absolutely does. You can spin them on the ARM nodes if you like, on your laptops if you like, on your regular x86 servers, but don't expect miracles unless you have a lot of CPU, a lot of RAM, and a fast storage. Simply, you have 3 replicas. When a first write is set to the Ceph cluster for some object which is modified, it goes to what is called a primary OSD, let's say a primary SSD, for example, and then Ceph will create additional 2 replicas if you have replica size of 3. And only when all the 3 OSDs or all the 3 storage devices have sent the acknowledgement only then actually to each other, let's say, only then the write acknowledgement is sent to the client. So client needs to wait for the network latency between OSDs for the data to be sent, data to be written to, and only then it will get the acknowledgement. So, for example, if you're using NVMe devices, which some of our community CloudStack users are using, you can expect very good latencies, but this is still like 5 to 10 times penalty if you compare the native NVMe latency, which goes like 20 to 100 microseconds. Realistic latency what you can achieve are like these, but these are actually extremely good, I would say, for a distributed storage. Now, if you are mixing hard drives and SSD drives, this is something I was getting with a very small Ceph cluster, which hard drives use primarily, and SSDs for the journaling. So it is awful, if I may say like this. If you're actually expecting performance, you will not get a lot of performance there. Also, never, ever use consumer SSDs. I have a story to tell. Somebody from one of my companies where I was managing Ceph cluster thought to just give us certain SSDs, pro version of certain vendor, but those were consumer SSDs. Long story short, after 3 weeks, we had something like 7 to 10 roughly completely dead SSDs. They were used only for journal. It was not really heavy there were no heavy write operations to the cluster, but simply they were not meant to be used in that ways because Ceph uses OD sync flags and some other things to directly avoid SSD cache and write really to the memory without actually writing to the actual cache of the SSD drive. And simply, when you do fdisk -l, you see like 2 megabyte partition instead of whatever number of gigabytes. They went completely dead. And after that, they actually, some guys listened to us and took the proper enterprise models. Interesting thing, if you have too many parallel streams, which is effectively something that Ceph manages very well, when you have many sequential streams, again, which are very good in general, any kind of storage can handle that properly. When they interleave at the backend storage, you have effectively a purely random I/O. So again, forget about hard drives, erase from the history. They are awful devices. Been nice so far, but now that we have SSDs and NVMEs, simply avoid them. Something I want to also mention, Ceph was so far until maybe 2-3 years ago, it has been, again, unofficially considered unsuitable for any serious random workload. If you dig up reference architecture guides from different vendors with Red Hat, so from Quanta, Compute Technology, Dell, or somebody else, you will see all of them lacking. There is no random I/O benchmarks. There are only sequential benchmarks. And actually, I believe, Quanta, Cloud Technology, or somebody else who actually explicitly written that Ceph is not yet considered suitable for random I/O workload. Now, this was like 3 years ago and more with older pre-Luminous, pre-Blue Store releases. And I can vouch for that. I was in that era, if you like. And I can say I had a lot of pain at that time. But things had actually changed really, really seriously in the last couple of years, especially with the new Blue Store being introduced as the backend for the actually like a storage backend, the way how the Ceph will store data on each OSD. So effectively now with the Blue Store, we are writing directly to a raw block device, which is effectively a raw partition of the Ceph, with only one small chunk of that being used for RockDB versus previously used LevelDB. And you could theoretically, still let's say the raw data will be on the block partition, let's say SSD or hard drive, God forbid. But you could put your BlockDB, which is effectively storing just a little bit of needed metadata about the OSD or the journal for that RockDB on a different devices. So, for example, hard drives. Here you can put the metadata database on the SSDs and the journal on NVMEs, for example. But again, avoid hard drives. Now, with these recent releases, it became much more possible, if you like, to unleash pretty much full performance of the SSDs and NVMEs, which definitely you could not do previously due to simply software constraints and architecture and different things. Throughput has been increased from at minimum 40% to realistically 40 to 200%. In some specific RADOS workloads, it went up to 300%, which is kind of a crazy. and the latency, which is one of the main obvious measurements of your performance, went down by those numbers when compared to the previous older file store. Let's say like a storage backend on a previous release, how the data was stored with the XFS file system and stuff like that. So really huge performance. And this is just with the Blue Store. A lot of other changes have been done. So, for example, we also now have explicit memory management per OSD because the Blue Store runs effectively in the user space. So you can actually set kind of a target memory limit for each OSD, while previously it was effectively XFS page cache, if you like, in some sense, which was managed by kernel. There is no way to explicitly control the memory, how much memory your OSD can take, especially in recovery scenarios, which they need like double the normal space. There is data metadata checksums, which came with a Blue Store, compressions, LZ4 and Snappy and some other things. The thing is, which is not yet there, is unfortunately that still all the data is read only from the primary OSDs. There is no it's questionable if this will be actually changed at any later point in time. Still, the data is only read from the primary OSD instead of being possibly, read from other replicas. So yeah, mostly that's pretty much it. Those are some of the things, some of them from the community experiences and advices, if you like, best practices. Some of that is from my own positive and less positive experience from last years ago. I'm not speaking about this specific slide, but in general, what I have kind of shared with you so far. Anyone willing to kind of give Ceph a spin? We actually have three-part monster, article, step-by-step guide, which you can pretty much just copy-paste with more than enough of explanation of actually what are you doing and what are the caveats you can see. So yeah, that's pretty much it for this time. Any questions?
Yeah, I know Libvirt has been able to do multiple monitors on the X1 configuration file for years now. Do you know if there's been any push for getting CloudStack fixed to add multiple monitors when you add the primary storage?
Multiple, sorry, what? I didn't hear that.
So when you add primary storage to CloudStack,
okay.
You say to do a round robin local DNS, right?
Okay.
Do you know if there's any sort of development time into just adding multiple monitors?
Yeah, for now, obviously, as you can imagine, that's not supported. I assume it would be possible, but again, you need to see how that works with Libvirt. It's not only, we can probably easily, support that in CloudStack, but is it really supported by the Libvirt to be able? Because for every monitor IP you create, there is obviously a storage pool created in Libvirt, and there is also a secret created there, and so on and so forth. So, this would kind of imply additional, if you change IP, for example, to another IP of the monitor in sense of, supporting it, there is an additional storage pool being created. So I guess that it might be doable, but yeah, for now, I guess we have a couple of big users actually, which you guys are probably aware in the community, which are big Ceph users with CloudStack. For some reason, they didn't consider doing that, although they did a lot of improvements and fixes. So I'm kind of thinking, again, that's just my personal thinking, that, round robin is kind of good enough because you don't really get your monitors nodes to really go dead every day. But yeah, I mean, that would be a valid improvement for sure. Cool. Any more questions? Cool. Thank you for your attention. And again, I'm just kind of reminding you, to remind you for the hackathon tomorrow, and I'm more than kindly asking anybody willing from the CloudStack users to give us some very short interviews just for the actual CloudStack project, so to move things even a bit more forward. Thank you.